Welcome back. This is our third day of integration. I'm going to be talking about how we can solve more advanced integration problems through a process called U-Substitution. So the objective is to undo chain rule, basically, with integration. And we'll be doing that with constant multiples, trig functions, and definite integrations. That's integration that has bounds. So here's everything we've covered so far. My first one here is what we call the first fundamental theorem of calculus. It says as long as I integrate a function, we'll end up from starting with a derivative to an original function, and then have to plug in an upper bound and subtract a lower bound. So if we integrated x squared from 2 to 3, I would end up with x cubed over 3, and then have to plug in your bounds. This second one is power rule for integration. So it just says add 1 to the power, divide by the new power, divide by dx, and then add c. Hi, Jenna. And we've got our 6 trig functions, which are really just working backwards. So if I integrate sine, I'll get negative cosine. If I integrate secant and tangent, I'll get back to secant. Again, all of these integration rules are just asking what did I derive in order to get here. So I would have had to derive tangent in order to get secant squared. I would have had to derive sine in order to get cosine, derive cosecant to get negative cosecant cotangent, and derive cotangent to get negative cosecant squared. So everything we've done so far is really just working backwards. Any questions on anything we've covered from the previous 2 lessons? So any of the rules that are showing. Okay. So new stuff then. When we are deriving with chain rule, we end up taking an inside part of a function and leaving it alone as we do power rule. So we multiply by the power, decrease the power by 1, and then we go back to that inside function. There we go. Okay, we go back to that inside function and derive it. So with chain rule, we have to multiply by the derivative of the inside function as our last step. Okay, I've got my extra dx here because that would be the derivative of the inside function of this inside function. So if I derive x cubed plus 4x minus 6, I get 3x squared plus 4. If I derive 3x squared plus 4, the inside part is x. So I'd multiply by the derivative of x. Okay, so with chain rule, I'll have to work backwards with integration, which means we have to figure out what the inside function would be. So for us, if I was given everything that we ended with, my inside part of this function is x cubed plus 4x minus 6. My derivative of that inside part is 3x squared plus 4 dx. So I can then make a substitution. So I'm going to replace this x cubed plus 4x minus 6 with u, and replace the derivative with du, which will give me a new equation for the integral in terms of u instead of in terms of x. If I do, this will become 20u to the 19th power du, and then with our rules for integration, I'll add 1 to the power, divide by the new power, and divide by du in this case. Will give me u to the 20th power plus c. And then I can go back and substitute because u is x cubed plus 4x minus 6. We can substitute that in for u. So this will be x cubed plus 4x minus 6 to the 20th power plus c. So I had left this in the original form, which made it a little bit easier to see what the inside function and its derivative would be. You most likely won't be given that. So if I had simplified this for my answer, this would have been 60x squared plus 80 dx that you would have seen on the outside here. I would still have to be able to figure out that my inside part of the function is x cubed plus 4x minus 6, derive that to get 3x squared plus 4, and then I'd have to pull out 20 in order to replace this du, which we'll see in the next slide. So some notes. After we do our substitutions, we need to have everything in terms of one variable before we can integrate. If you've got a mixed some u's and some x's, then we won't be able to integrate. We also need to substitute for the original inside function for this to work. So there may be some trial and error involved in trying to figure out which inside function was the original inside function that we derived with chain rule. Okay, here's a couple more examples. So for this one, when I try to integrate, my inside function is the piece that's inside these parentheses. This is 4x squared plus 5. When I derive it, I'll get 8x dx, but I don't have an 8x dx on the outside. I only have 1x dx. So what I'm going to do is I'm going to multiply by 8 and divide by 8. That way I'm not changing the original problem. Since when we derive with a constant multiple, if I derive 4x, I get 4. The constant multiple stays the same. I can pull this 1/8 out of the integral. That won't change what happened to my derivative. That leaves me with the 8x dx on the outside that we need to substitute for this du. Okay, so now when we substitute for u is 4x squared plus 5. And our du is 8x dx. So I can rewrite this equation in terms of u. Then when we integrate, I'll add 1 to the power, divide by the new power, so this becomes u to the 8th over 8 times the 1/8 that we had on the outside. Will give me u to the 8th over 64. Okay, if we do that, we can resub for u. Our u is 4x squared plus 5, so this will become 4x squared plus 5 to the 8th power. Over 64. Okay, same thing with these trig functions. So I'm given the sine squared of 4x times cosine x dx, and I want to integrate it. So my inside function is this part that I am squaring, is all of sine 4x. If I derive that, I'll get 4 cosine 4x dx. I've got a cosine 4x dx, but not the 4. So I'm going to multiply by 4 and divide by 4. That way I don't change the original problem. But I'm going to use that 4 that I'm multiplying to be part of my u prime when we substitute. So that'll become this sine 4x is this sine 4x that I'm squaring will become u squared. This 4 cosine 4x dx will use this 4 and this cosine 4x dx to substitute for u prime. And now I can integrate normally. So when I integrate u squared u prime, I'll get u cubed over 3 plus c. So this part will become this part. Okay, then I multiply by the 1/4 I had on the outside to give me u cubed over 12. And then we'll resub for u. Our u is the sine of 4x. There we go. U is the sine of 4x. So I'm going to replace this u cubed with the sine of 4x cubed to get my final answer. Any questions on either of these two?
Mr. Brandon,
Yes.
if you're doing a substitution for u prime, for trig function, do you have to use u prime?
So we're always going to use u prime because we need to be able to get a dx that we can substitute for in terms of u. Okay, good question. Anything else? Okay. Then one more. If I've got bounds, we're going to do everything the same way that we just did, but at the end we'll have to plug in our upper bound and lower bound. The cool thing about this is when we resub for u, our bounds change. So we actually don't have to go back and resub for x if we've got bounds. As long as we change our bounds to be in terms of u instead of in terms of x, we can just get a number. So here's what that looks like. If I wanted to integrate this, I've got my inside function here, 4x cubed plus 2, so that will be my u. When I derive it, I get 12x squared. That 12x squared is not quite the 6x squared dx that I have on the outside. Dx. Okay, because I don't have the 6x squared that I need, I have 12x squared. I'm going to have to multiply by 1/2 and multiply by 2. That way I don't change the original problem. And then that 2 times 6x squared will be the 12x squared that I need for my derivative. Okay, so that leaves me with I've actually got a mistake on here, so I'm going to change this as we go. Okay, so I need the 2 and the 6x, so that means my 1/2 is going to be on the outside here. So when I integrate, this will be u to the 6 over 6 times the 1/2 that I have on the outside will be u to the 6 divided by a 12. And then I can plug that in to get an answer. So I have 34 raised to the 6th power over 12 minus 6 to the 6th power over 12. It's going to be a crazy large answer, but let's throw my dx here too, because that matches everything else we've done. Okay. So what's different here, what I want to focus on is this third step. So when we went to substitute, I had my u is my inside part, my derivative of u, and then in order to substitute, I had to multiply by the 2 and the 1/2 because I didn't want to change anything. When I do and go to substitute for u, my bounds were originally in terms of x, so I've changed them to be in terms of u, which means I'm going to use this equation, u is 4x cubed plus 2, to change what these bounds are. So if I plug in 2 right now, then my u would be 4 times 2 cubed plus 2. So that's 4 times 8 plus 2. 4 times 8 is 32, plus 2 is 34. For this 1, I'll do the same thing. 4 times 1 cubed is 4, plus 2 is 6. So my new bounds are from 6 to 34. And if I do that, then I never have to change back in terms of x. I can solve this in terms of u and still get the same decimal answer. Any questions on anything from today? Okay. So I've got a bunch of practice problems that we'll do for homework that are pretty much the same as these slides. And I'm going to link the updated PowerPoint on both WeChat and Skype. If you guys have questions, please let me know over the weekend. This one will not be due until Tuesday of next week because I still have to talk to the other class with it as well. Okay, thank you guys so much for coming, and I hope you enjoy the weekend.